The Perseus is now connected through a long cable out the window to the whip antenna with the isolation toroid near the antenna. I'm listening on low frequencies. This is an English speaking station as 252 kilohertz. I will connect the Perseus screen, the connector on the BNC, to the heating system of the house to see if this still makes some difference. Now it's connected and disconnected. Connected, disconnected. It looks like about 2 decibels difference. Not much. And of course, other long wave stations that are not so far away, they are stronger. This is also an English station. And here are NDBs, I guess. This must be a local thing. So I step up in frequency. I think I can hear some music in the noise. And again, I connect the BNC connector to the heating system. Connected, disconnected. Connected, disconnected. It makes a very small difference. And I cannot hear anything on the medium waves. But this here, it looks like noise. I can hear a distinct tone in it. If I increase the bandwidth, it becomes more obvious. I don't know if this could come from this house. Probably it does not, because I don't hear anything like this inside. The antenna is here, about 25 meters from the house. And the isolation toroid, cannot see in the camera, yes, here it is. I will move the antenna another 10 meters away and then check whether this interference has become weaker. As you can see, there is no difference at all. It was already outside the local fields of the house, and this interference must come from much further away. I don't know what the origin might be. I could walk around greater areas to see if I can locate it. But it's not very strong anyway. Here the coaxial cable leaves the house, like that. And some meters away I can check it with a magnetic probe. There is very clearly a lot of current flowing on this cable. If I tune the frequency, so it's obvious that the cable is sending interference out in the direction of the antenna. I'm not so far away from the antenna, it's standing here. When there is only about 2 meters, when I am about 2 meters from the end, the current starts to go to zero, because the capacitance between the cable and the ground that is further away from the house than the sensor, that capacitance is now very small. So the current becomes very small. And at the end of the cable, there is of course no current. It has nowhere to go. This antenna is a capacitive probe that couples into the waveguide, two-dimensional waveguide between the ionosphere and the ground. There is a big capacitor to ground from this sheet and a small capacitor up into the waveguide. I don't need to put something down into the ground to make a low impedance. The impedance of this capacitor is low enough. So this is a very convenient arrangement. It's just standing here. And I can move it to different places and see where there is interference. But this shows what the electric sensor is good for, and I have already shown how the magnetic sensor shows that the current is zero here at the end. Now I would like to bring the voltage down to zero here, and that could be done. This transformer, it provides very good isolation. As we can see here, I save this track data to memory, and then I can put the screen in here, and you can see at 10 megahertz it gives something like 6 decibels. That's the capacitance from here to here, which is similar in size as the capacitance right across the toroid from here to here. Much larger area, but much larger distance. So this transformer is good for isolation from DC to 10 megahertz. Transmission is another thing. It has a maximum at about 1 megahertz. Of course, I designed this for medium waves, and the attenuation is about 20 dB at 10 megahertz. That is possible to compensate with the amplifier at the whip antenna, if desired. The conventional solution to isolate antennas is to wind the coaxial cable on a toroid. This toroid has not a coaxial cable wound on it, it's just a twin line, a balanced line, but this doesn't matter at all. If you think about what is sitting in the end of it, it doesn't matter if you have from here white to red or if it is from white to white, because the very thing that this inductor does is to isolate the two sides. The transmission, as you can see, is very good from DC up to 10 megahertz. It's about 2 dB loss at 10 megahertz and no loss at all at DC. Now I have connected both wires to the center conductor of the input and output of the network analyzer. That's to measure the isolation. The markers are on 1, 2, 3 and 4 megahertz, and you can see that at the track starts at 300 kilohertz, where the isolation is about 20 dB. It means that the impedance is 500 ohms. That is far from enough to suppress the interference. At 10 megahertz, this isolation is perfectly adequate. But normal solutions means much fewer turns than this, because you cannot get so many turns of coaxial cables on a reasonably sized ferrite core. Here is a similar ferrite inductor with a transmission line on it. I'm measuring isolation. This is a low frequency ferrite. I don't know exactly what it is, but it's much higher permeability and much higher losses on high frequencies. And you can see it behaves quite differently. It gives 50 decibels at 300 kilohertz, and it gives 40 decibels at 3 megahertz. So this would be okay on medium wave and long waves, but of course it doesn't isolate at very low frequencies. Now I have connected these two toroids in series, and maybe you find this result unexpected. There is a resonance peak at 3.5 megahertz where it isolates only with 30 dB. That's because this toroid behaves as a capacitor, and it makes a serious resonance with this inductor. I have to load it. I can hold on the center like that. Then you can see when I hold on it, this peak moves. Now the appropriate load is not my hand. I will find something else that makes this better. With 4.7 kilo ohms across the high frequency toroid, the attenuation looks like this. It is 40 decibels from 10 megahertz down to perhaps 200 kilohertz. So this is the tool that should allow me to feed the amplifier with DC from inside the house, so I can eliminate the battery. Here is the complete isolator, the two transformers and two 10 kilo ohm resistors. And it gives nearly 40 dB at 10 megahertz, and then better than 40 dB below 5 megahertz, down to maybe 250 or so. Now the transmission, as you can see, it's not ideal. It is the insertion loss is very close to zero, below 1 megahertz. At 10 megahertz there is about 3 decibels loss, And the reason is that the impedance is about 120 ohms and not 50 ohms. That's the impedance of the twisted pair. So I should use a twisted pair with a thinner isolation. This is wire wrap wire, and maybe one of these and one enameled wire would give me about 50 ohms. I will try that some other day. I can show better that the problem is really the impedance. If you look at the Schmidt diagram, and then I connect a resistor at the end point instead. Now I have terminated this isolator with a 120 ohm resistor. And you can see on the Schmidt diagram that I have 120 ohms from DC to 10 megahertz. So the losses is a mismatch loss, and it's not harmful because it's on the right side of an amplifier in the active antenna. I have now replaced the toroid transformer with the 2 toroid isolator, and the level now at 1.2 megahertz is maybe 3 dB higher because of the lower attenuation. The time is 20 minutes past 6 p.m. and we start to get medium wave stations. I can go down in frequency, and you can see here at very low frequency the level is much higher than before, and if I listen to it, it sounds like what my house is emitting, because the attenuation in this isolator is not good at very low frequencies. It should be okay from about 200 kilohertz. Here now I can connect ground to the parcels using the plumbing of the heating system of the house, like this. And it's obvious that even at 400 kilohertz, this is not as good at all as the transformer. I go a little bit higher, let's say here. This is 750 kilohertz, and I connect the ground again. And here it doesn't make any difference anymore. But I want my antenna to work all the way down to 50 kilohertz or so, and I want it to be powered from inside the house. So I have to do some more tricks to improve isolation. Here is one more isolator. This one uses enameled 0.35 millimeter wire. So there are a few more turns on these toroids. Performance is like this. This is the isolation it provides, and it's about 40 dB from 10 megahertz all the way down to 2 megahertz, and then it improves and goes to 60 dB at 300 kilohertz. This is the transmission. It is the loss is about 1 dB at 10 megahertz, and it goes towards 0 at DC. The impedance of the twisted pair is maybe 65 ohms, 60 ohms something. You can see the center of the little circle near the midpoint of the Schmidt diagram. So this is an improved isolator, although it doesn't really matter for this purpose. This is DC to 500 kilohertz, and I'm listening at the station on 153 kilohertz. I will now insert the isolator at the parsecs, so there will be now two isolators, one in each end of the coaxial cable. And the situation is a little better. I can get an idea about what the isolator does by connecting the screen on both sides. I do that with a simple wire. Here you can see what the isolation provides. So it's about 10 dB at this point, and it brings the problems at, say, 70 kilohertz here. I should listen to something sensible, and then I short the isolator. I can connect the chassis of the parsecs to the heating system ground of the house, and you see that improves a little bit also. What is needed now is a better grounding of the screen of the long cable. On higher frequencies it is well grounded because it has a large capacitance to ground, but at 50 kilohertz that capacitance isn't really high enough. I would need a traditional grounding, dig a hole and put some metal down. So I will use the sensors tomorrow and try to find out how to do this best. The isolators are wideband. I'm now listening on 15.58 megahertz. And if I disconnect the cable to the parsecs, I can see that the noise floor doesn't rise much. It means that the amplifier, the source follower, should have a little bit more gain, at least at higher frequencies. So now that I have a DC connection to it, I will rebuild that amplifier. I have modified the amplifier. It's no longer a source follower. The source has 100 ohms to ground in parallel with 0.33 microfarads. The gate is on the antenna, and there is 220 ohms from the whip to ground. The drain goes directly to the coaxial cable. So this is a very simple thing. In the other end I have added capacitors and a 330 ohm resistor, so it will be possible to feed DC into the drain. This is DC to 500 kilohertz, and if I listen at some place where there is more or less no signal, it sounds like this. So there is a signal, obviously. Here. I short-circuit the isolator by connecting the two BNC connector screens to each other. And you can see it makes a difference, particularly below 100 kilohertz. I can connect the Paracels screen to the plumbing system of the house, the ground point. Now it's connected and now it's disconnected. It doesn't make much of a difference. I can connect the screen of the coaxial cable instead. And it makes some difference, but not much. Now it's connected, disconnected. Look at 50 kilohertz. And I can listen at higher frequencies. The medium wave, a lot of stations. And it looks very quiet and nice. Step up.
Die sinnliche Fülle des Lebens im Alter.
And the end of the medium wave is here. This is the last station here. And I can go further upwards. And I have no idea what we have here. This looks very bad. It's in the amateur band. What's that? I connect. I think this is a real signal. Something transmitted on the ham band. Here is some funny thing. These, I think they are familiar to most HF listeners. Here is a broadcasting band. Sorry, I meant to click here. And here is something. It's a digital transmission, but we have ordinary AM here, 7.3 megahertz. And so this is a broadcasting band again. I think. .7 megahertz.
plug, on a parlé de navette. 您好。
As I understood the stigmata, we're talking about the wounds.
So we still have signals at 15 megahertz. It's now midnight, 20 minutes past 12. The amplifier is very simple, just a single transistor. This is the output that goes into the Perseus. The peak-to-peak amplitude is about 160 millivolts. That's well within the linear region of this transistor. This is very low frequencies, so there is no attenuation in the isolators. And there is not much signal energy on higher frequencies. Here it's 11 megahertz about is the dominating, like that. About 11 megahertz is the dominating signal in the HF region. There are some pitfalls. Here you can see a big interference on the long wave at 200 kilohertz approximately. The isolator is here, but nothing is connected to the output. The power supply here is not switched on, but the cable from it, the red cable here, it happens to go very close to the power supply cable of the Perseus. So I can lift it away. And it's much better now, but it's still not good. I put it back and demonstrate what happens if I make a short circuit here. And you see, now it's okay. I need a bigger capacitor or rather a better filter for the power supply as it enters the center contactor of the coaxial cable. Here is 100 microfarads. And that is not quite enough, not at the very low frequencies. So I will make a filter on this device. With 100 ohms plus the 100 microfarad capacitor added, there is now nothing when the antenna is not connected and the power supply is off. And that is with the DC supply cable in the most unfavorable position near the power supply cable of the Perseus. So I can remove it and place the power supply elsewhere, like that. The Perseus is behind this window and the cable comes here. The cable is isolated in both ends, both at the antenna and at the Perseus, but it goes into the house and it couples capacitively to all the fields that are inside there. And that is very clearly sending currents onto it. So This is undesired and it puts requirements on the isolator near the antenna. There are cheap and easily found current sensors, or H-field sensors, or magnetic sensors, what you want to call them. This is an AM radio. I switch it on and listen to the cable with it. So it also shows that we have a problem. I can tune the frequency a little bit. So you can use that as a tool to check your cables for the antenna. Now the isolator is here, and there is the house, and the magnetic sensor. It shows a little current, but very much smaller than before. The antenna is not grounded at any point. It's just capacitively coupled to ground, which means that at very low frequencies up here, the impedance to ground is very high. It's only maybe 100 pf or something. That is the capacitance. I haven't measured, I don't really know. And then there is the isolated cable. It should also be grounded, but it's just laying on the ground, so it has a capacitive coupling, which isn't strong enough down here. It's perfectly adequate on medium waves, but I want this antenna to work also at very low frequencies, so I will add a ground point. This copper tube is about 70 centimeters. I will bring it down near this tree where I know there are no stones in the ground. The copper tube is now about half a meter into the ground. I can listen to the wire that comes from it. It's about that. And the wire, the coaxial cable to the antenna. It has clearly less current than this wire. And this is at some medium wave. You see, it's at 1.5 megahertz. So the difference will be far more significant on very low frequencies. I will go inside and have a look at the screen. Now the ground point is in place, so the isolated cable is grounded with a half a meter copper tube into the ground. I had expected some improvement around here, but I don't have the old screen, so I cannot comment on it. But as you can see, there is still a lot of interference. And if I listen here, it's clear what type of interference it is. But we have signals. So here is this French guy. I have now improved the ground point by putting another copper tube twice the diameter, about to the same depth, into the ground. That should give about 3 times larger area, so maybe 3 times lower voltage or 10 dB lower noise. We can start to see, for example, this interference goes down and up and down and up and down, and here it starts to go away. That looks like some neighbor using a switch power supply of some kind. The level here is now like that, maybe 28 dB. It was about 40 dB without the ground point. If this were a permanent installation, I would add the ground point for the whip antenna itself also. But now this is just an experiment, so the next thing I will do is to move the whip antenna around to see how the field differs. I can move it some maybe 20 meters in different directions and look at the variations of, for example, this noise floor. Maybe I can see in which direction it increases or decreases, so I know which neighbor to pay a visit to. It is an electric field, so it is probably very easy to eliminate it. So I get an overview of the noise floor and the signals in daytime. It is 4:30 in the afternoon now, so the sun is still reasonably high. And here we have a peak. This has to be an interference of some kind. I will open the bandwidth. So it's clearly not white noise. You cannot hear that through the camera because the quality isn't good enough for that. It's at 1.3 megahertz. It has a peak. I will enable the S-meter graph. In decibels and magnify a little bit. The white track is the peak and the yellow track is the RMS power. Something like that. So we have now a level of 36 dB, and I will go outside and move the antenna in some direction. The antenna is now 20 meters further away from the house. That is in direction southeast. And there is no difference at this. The antenna is now 20 meters away from the original position in direction northeast. And the interference is clearly stronger, about 3 decibels. So it is standing here now, and it's about 10% closer to the industrial facilities. You can see maybe through the tree. This is my neighbor. He is making, he's growing pigs, and he has a lot of fans and many other stuff in there with switch power supplies, and he has computers and he has many things. So it would be a problem if I was a serious medium wave DXer. I would then tell him that he has poor protection against lightning. He needs to probably put the ground wire to metal structures on the roofs of his buildings or something that would confine the electric fields. I could go there with the electric sensor and see where the strong fields come from, to help him to make his property a little bit safer should there be a thunderstorm here. The antenna is now about 15 meters away from the original position, but in the opposite direction with respect to the farmer. And you can see the RMS noise is a little lower, but I can hear it sounds a little bit more like a white noise now. On very low frequencies, it's a little bit different. The level all the way here is only 10 dB, so this is an improvement. There were these things that stepped up and fell down, stepped up and fell down, some kind of switch power. I'm 35 meters further away from the farmer, and it seems that it came from him. The time is now 5 o'clock in the afternoon. The long waves is of course perfect in quality. This is an English-speaking station. I don't know what it might be. 207 kilohertz. Medium waves, QSB. I can hear something talking. Higher medium waves, not much. So you can see the noise floor stays fairly low. Here is a broadcasting band. 6 megahertz.
11-й гвардейской особой механизованной бригады и 103-й гвардейской особой мобильной бригады.
There is no problem with interference anywhere anymore. I'm now on a fairly quiet frequency, 756 kilohertz, a German-speaking station. 15 minutes past 5 in the afternoon, so the medium wave is starting to come through. I will move the antenna much nearer the house to see where is the limit where the interference from all my fluorescent lights and things start to hamper the reception. The antenna is now about 10 meters from the house. This is a position where there are electric fields, but they are horizontal, and the antenna, the whip, is sensitive for vertical fields only. And I happen to select a frequency where I don't see any interference, but I can see lower frequencies are damaged. So it's worst about here. I need a narrower bandwidth to see on the S-meter what happens to the noise floor. So, like this. And I will move a little bit away until this interference has disappeared. Now the distance is about 15 meters and the level is something like 6 decibels lower. So it means I would have to go about 10 meters further away to make this completely disappear. Here is 20 meters from the house. This interference is still significant, but much smaller than it was 10 meters from the house. Sorry. I leave the mouse on the level we have and move the antenna further away. Now the antenna is 25 meters from the house. This is the position where I originally stated it is 30 meters away. I didn't measure it very accurately. The interference from the house can still be heard, but it's not really dominating. So this is about the kind of distance required from a noisy house like the one I live in. At 6 o'clock p.m. the noise level at 1.3 megahertz is about 30 dB RMS, and that is essentially due to interference from the nearby farmer. I will look at this a little bit later when we have medium wave stations to see whether this really matters or not. Time is now 9 p.m. It's nearly dark outside and there are a lot of stations on the medium waves. The noise floor seems to have become a little bit lower. I don't know whether the farmer is still running his equipment or whether the actual noise floor on medium waves is lower at this time of the day. The antenna is now about 20 meters southwest from the position it was originally, just before this I moved it. So it's now further away from the farmer, in the position where the noise was a little bit lower in daytime. The S-meter shows an improvement, but it's not quite correct because there is now also a carrier that contributes to the S-meter reading. So I wait for a while to see whether there is a QSB minimum to read the background noise level. Here, perhaps 29 dB, approximately. This means that this antenna is good enough, but there is no margin in the suppression of neighbor-induced interference on some frequencies, and this is one of them. Local interference, as has been shown before in this video, depends very much on the distance. It's because it is local field, it's dipole fields that don't radiate. A very small movement, like in this case 50 meters, makes a huge difference on the level of the interference, but the interesting signals are the same. That means it is possible to use two antennas and to cancel the interference without losing much of the desired signal, regardless of what direction it comes from. With some luck, the desired signal could be a little bit stronger if the antennas add in phase. And it could be a little bit smaller if the antennas add out of phase. So this is one opportunity to improve reception a little bit in difficult circumstances. The other option we have is to use magnetic antennas. They may perform better. That depends on the nature of the interference source.